Imagine this. Traveller, you arrive here as though the cosmos itself nudged you toward a quiet question. A fragment of another star drifting between Mars and the Sun. A shape too long, too bright, too silent. And what are the odds a 1 in 20,000 trajectory brushing past 3 worlds, as if following a script older than our sky observers speak of a glow that should have been green yet burned white. A whisper hidden in background radiation. A possibility no telescope wants to name. What if this wasn't just a comet, but a message moving in plain sight? Stay a while, traveller. The events surrounding the Mars flyby of 3 Atlas on October 4, 2025 have become one of the most discussed and scrutinised episodes in recent observational astronomy. What began as a routine series of navigation images captured by the Perseverance rover quickly expanded into an international debate, elevating questions about instrumentation, data transparency, and the interpretation of interstellar anomalies. The elongated streak recorded in the Martian sky serves as an informative case study, illustrating both the strengths and limitations of modern planetary observation systems. The Perseverance rover's navigation camera, known as NavCam, is designed primarily for hazard detection and operational planning. Its purpose is not to gather detailed scientific imagery, but to deliver dependable contextual data about the rover's surroundings. These images are low in resolution, monochromatic, and optimized for rapid transmission rather than precision analysis. Despite these constraints, the camera was pointed toward the Martian sky during the closest approach of 3 Atlas, resulting in a series of frames that inadvertently captured a fast-moving luminous object. When these raw frames were released through the standard public access pipeline, amateur astronomers began stacking them, a widely used method in astrophotography designed to enhance faint signals while reducing noise. The resulting composite image revealed a long bright streak with a white core and faint green edges. This observation was immediately notable because typical stacked images of distant comets tend to produce either a roundish blur or a uniformly extended diffused shape. The ratio of length to width in this particular case, approximately 4:1, was unusually high, prompting early speculation. One of the first interpretations came from Harvard astrophysicist Avi Loeb, who argued that the elongated feature was entirely consistent with the motion blur. At the object's estimated velocity, roughly 67 km per second relative to the Sun, and even higher relative to Mars, the displacement over a 10-minute interval could exceed tens of thousands of kilometers across the sky. Loeb's calculations showed that a displacement of approximately 50,000 kilometers would produce exactly the sort of streak observed. His position reflected a conservative and well-supported interpretation grounded in established imaging principles. However, this explanation faced immediate challenges from other researchers. Some questioned the consistency of the colour distribution. If the object's coma were emitting green light due to molecules such as CN or C2, the central region of the stacked streak should exhibit amplified green at the nucleus. Instead, the composite image preserved a white centre with green only along the fringes. Critics argue that this suggested the green emission might not originate from the nucleus itself, but rather from a broader, perhaps irregularly shaped region, surrounding a more reflective core. This raised the possibility that the observed structure represented not merely motion blur, but a physically elongated or a symmetrical body. The scientific debate deepened when contextual chemical data were considered. Earth-based spectroscopy in the weeks preceding the Mars flyby indicated abnormally high production rates of nickel without the accompanying iron signatures typically associated with cometary sublimation. While rare natural mechanisms could theoretically explain nickel-rich emissions, the required conditions, especially at such large heliocentric distances, were inconsistent with known cometary behaviour. These chemical anomalies remained unresolved during the flyby, further complicating efforts to interpret the elongated feature in the NavCam imagery. At the same time, the absence of high-resolution images from major space agencies added another layer of uncertainty. NASA experienced a government shutdown beginning October 1st, which halted the processing and release of images from instruments such as HiRISE. But even more surprising was the simultaneous lack of released imagery from ESA's Trace Gas Orbiter, China's Tianwen-1 mission, and the UAE's HOPE orbiter. All four agencies have historically demonstrated reliability in sharing Mars images promptly, often within days or even hours of acquisition. The temporary silence therefore appeared unusual, especially given the scientific value of an interstellar object passing near Mars. Amateur astronomers attempted to bridge the data gap by gathering Earth-based observations during a lunar eclipse on September 7th. The dimmed sky allowed for longer exposures, producing additional evidence of a possible colour shift in the object. Yet these observations also raise new questions. If 3I Atlas were indeed fluorescing green, the expected chemical signatures should have been stronger. Instead, spectroscopic data continued to show lower than expected levels of the relevant molecules. This mismatch between observed colour and inferred chemistry further complicated attempts to build a coherent model of the object's behaviour. From an analytical standpoint, the elongated streak seen from Mars must be understood as the product of several overlapping factors: the limitations of the NavCam instrument, the motion of the object relative to the rover potential Comet asymmetry, and uncertainties in the object's chemical emissions. Each factor individually could influence the appearance of the streak, but only by considering them in combination does the full complexity become apparent. Without higher quality images, it remains difficult to determine whether the observed structure was entirely consistent with natural cometary processes or indicative of an unusual physical configuration. The Mars flyby therefore represents a moment of incomplete data rather than definitive discovery. It demonstrates how even with advanced observational capabilities across multiple planets, gaps in publicly available information can lead to prolonged scientific uncertainty. The lack of coordinated imagery from Mars orbiters limits researchers' ability to validate or refute claims regarding the object's appearance, and the raw rover images, though intriguing, are not sufficient to draw final conclusions. Ultimately, the elongated streak recorded by Perseverance serves as a microcosm of the broader challenges inherent in studying interstellar visitors: limited windows of observation, rapidly changing environmental conditions, and incomplete datasets that often raise more questions than answers. Whether the Mars images captured a simple motion-blurred coma or hinted at a more complex physical structure remains unknown. What is certain is that the flyby dramatically increased scientific interest in 3I Atlas and motivated deeper investigation into its behaviour as it approached perihelion. The debate surrounding the elongated appearance of 3I Atlas in the October 4th, Perseverance images crystallise into two opposing interpretations, each grounded in different assumptions about imaging, physics and cometary behaviour. At the centre of this controversy lies a single question: what does it mean when a distant interstellar object displays a structure that defies conventional expectations? The answer depends not only on what the images show, but also on how we interpret the processes that produced them. The standard explanation, supported by many professional astronomers, is rooted in the physics of image stacking. The Perseverance rover's navigation camera was not designed to resolve fine detail at tens of millions of kilometers. Its angular resolution, about 33 milliradians per pixel, translates to roughly 12,500 kilometers per pixel at the distance of 3 Atlas during the Mars flyby. This means that any single frame is extremely coarse, far too coarse to capture the shape of a nucleus or even the structure of a coma. The key technique that enabled amateurs to extract a usable image was the stacking of hundreds of individual frames. Stacking reduces random noise by averaging across exposures, allowing faint objects to emerge from a noisy background. However, stacking also introduces temporal artifacts. If the target object moves during the acquisition window, its motion becomes encoded in the composite image. The streaked appearance of satellites photographed with long exposures is a familiar example of this effect. Avilob and several colleagues argued that the elongated 4:1 structure shown in stacked Perseverance frames is precisely the kind of motion smear one would expect from an object travelling roughly 91 kilometres relative to Mars when camera exposures span nearly 10 minutes. The math appeared consistent. At that velocity, the object would move about 50,000 kilometres in the imaging window, almost exactly the length of the streak seen in the processed composites. If this interpretation is correct, the images reveal nothing about the physical structure of 3I Atlas. Instead, they illustrate the limitations of trying to image an interstellar body with a navigation camera optimized for obstacle detection rather than astrophysical observation. However, not everyone accepted this interpretation. Dr. Horace Drew, an independent researcher with a background in molecular biology and a long history of analyzing unusual astronomical images, proposed a different reading. His argument focused not on the streak itself, but on the distribution of color within it. Enhanced versions of these stacked images showed a bright white central region surrounded by faint green. This green component was consistent with independent ground-based observations that suggested the presence of a nickel-rich coma, an unusual chemical signature for a comet. Drew pointed out that if the elongation were purely a stacking artifact created by the motion of a small white nucleus embedded within a large green coma, the resulting stacked image should be predominantly green along its entire length. Each frame would capture the coma's extended glow as the object moved, and stacking would accumulate those green photons into a long smear. The central white region would be diluted by the green emission. Instead, these stacked Perseverance images showed a dominant white core, implying, as Drew suggested, that the white emitting region might be physically extended. In other words, the object might truly be elongated and significantly larger than the surrounding coma. Critics countered that the colorization applied to the Perseverance images was not original, but rather added by amateurs. Perseverance's NavCam records only in grayscale. Any green in processed images is therefore an interpretive overlay, not a direct measurement of spectral content. Moreover, the brightness profile of a typical cometary coma is not uniform. The region near the nucleus is far brighter than the outer layers, meaning a bright central region would dominate stacked images even if green emission were present throughout the coma. The controversy deepened when amateur astronomers using Earth-based telescopes reported that 3I Atlas appeared elongated even when exposures were short enough to minimize motion blur. Some images showed a slightly elliptical white core surrounded by a faint green halo. These observations, though limited by atmospheric distortion and instrumental resolution, suggested that the elongated appearance might not be limited to the Mars images. But without standardized processing protocols or access to raw instrument calibrations, the data remained ambiguous. Central to the unresolved tension is the fact that multiple space agencies, NASA, ESA, CNSA, and the UAE took high-resolution images of 3I Atlas during its Mars flyby and released none of them. This absence of official data amplified debate over image interpretation. If professional imagery clearly contradicted the elongated shape implied by amateur processing, why not release it? If the images confirmed an unusual structure, why remain silent? The lack of clarity created an environment in which speculation filled the void that institutional transparency typically occupies. Ultimately, the dispute over the Perseverance elongation encapsulates a broader challenge: how science interprets incomplete or ambiguous data. In astronomy, observational limitations often masquerade as discoveries, and distinguishing artifact from anomaly is a core part of the discipline. Yet 3I Atlas complicates that task because its other properties, chemical composition, trajectory, and activity, are themselves atypical. Each unusual feature considered alone might be explainable. Together they invite deeper scrutiny. The Perseverance images remain a symbol of this uncertainty. Whether they captured a true physical structure, or simply the motion of a faint interstellar traveller across an inadequately equipped camera, they represent the boundary between what we can measure and what we can only infer. In that boundary space, certainty is rare, debate is inevitable, and the truth, whatever it may be, awaits better data. The behaviour of global space agencies in the days following the Mars flyby became one of the most discussed and least understood aspects of the 3I Atlas event. Under normal circumstances, missions like NASA's Mars Reconnaissance Orbiter or ESA's Mars Express release images within days, sometimes within hours of acquisition. These spacecraft operate with well-established pipelines for downlinking, calibrating and publishing data, and their images routinely appear on agency websites with little delay. This transparency serves many purposes: sustaining public trust, demonstrating scientific capability, justifying budgets, and supporting international collaboration. Yet after the closest approach of the third confirmed interstellar object ever observed, not a single high-resolution image was released by any of the 5 agencies positioned to capture it. This included NASA, ESA China's CNSA, the UAE's HOPE mission, and even Russia's participation through ExoMars instruments. The simultaneous silence was unprecedented. Each agency had strong incentives to publicize such a unique observation, and each had the technical ability to do so. Instead, they released nothing. No preliminary frames, no press statements, no analyst notes, and no confirmation of successful observation. NASA's explanation that the US government shutdown beginning October 1st forced staff furloughs that delayed processing was legitimate but incomplete. While a shutdown can disrupt public affairs work, it does not shut down automated pipelines for raw image posting. The Perseverance navcam, for example, continued uploading uncalibrated images to the raw feed automatically. The same principle applies to the Mars Reconnaissance Orbiter's HiRISE instrument. High-resolution frames are stored on board and can be downlinked without human presence even if they are not immediately processed into public-facing presentations. In the past, raw HiRISE data has appeared online during limited staffing periods, albeit without annotation. Thus, NASA's silence was unusual but not inexplicable. More puzzling was ESA's silence. ESA operates independently from US political constraints and typically publishes Mars-related data on regular schedules. Its teams had publicly announced plans to observe 3SI Atlas between October 1 and 7, using both orbital imagers and spectrometers. There was no shutdown in Europe, no budget crisis, no operational hindrance, yet ESA published nothing. This departure from routine practices broadened speculation, because ESA has historically been eager to share data from events of far lesser significance. China's silence added another layer of confusion. CNSA has spent years showcasing its Mars program as evidence of China's ascent in space exploration. Their mission logs for Tianwen-1 contain thousands of images published in near real time, often with high production value and strong nationalistic framing. Missing an opportunity to show the world a foreign interstellar object from an advantageous vantage point runs counter to China's usual messaging strategy. If the images showed nothing interesting, releasing them would still have reinforced China's scientific presence. The absence, therefore, became conspicuous not for what it concealed, but for being entirely out of character. The UAE's HOPE mission introduced still more complexity. HOPE is an explicitly public-oriented project with regular data dumps, an educational mandate, and a communication strategy designed to showcase the UAE's scientific ambitions. HOPE's spectrometers are well suited to measure gas composition in cometary Comet, and capturing even marginal data from 3I Atlas would have offered a chance for international recognition. Yet no statement acknowledged whether the observation succeeded or failed. Missions sometimes refrain from publishing flawed or incomplete data, but they typically acknowledge operational attempts even when results fall short. What makes the silence difficult to contextualize is that each agency normally acts with its own incentives, objectives, and constraints. NASA aims to maintain public support and scientific leadership. ESA prioritizes open science and multinational cooperation. China seeks prestige and geopolitical signaling. The UAE emphasizes visibility and scientific inclusion. Under these divergent motivations, coordinated silence becomes statistically improbable, unless driven by an external constraint or by independent decisions that coincidentally align. One explanation is mundane data processing takes time, and professional teams prefer to release fully analyzed products rather than raw material vulnerable to misinterpretation. This interpretation gains some support from past cases where complex observations, especially those involving multiple instruments, required months of calibration. Yet in those cases, agencies typically publish preliminary confirmations or contextual statements. Silence across all agencies is atypical even under heavy workloads. A second possibility is operational failure. Perhaps instruments malfunctioned during the flyby, rendering the planned data sets unusable, but simultaneous failures across 5 spacecraft of different designs from different nations, operated by different teams, is statistically improbable. Moreover, agencies generally disclose instrument anomalies, as transparency about technical performance is essential for mission credibility. A third interpretation is strategic caution. If early analyses revealed ambiguous or anomalous signatures that could be misinterpreted by the public, or sensationalized by media agencies, may have chosen to withhold data until conclusions could be vetted by internal review. This approach aligns with protocols discussed in astrobiology for handling unusual data sets with potential high-impact interpretations. While not formally binding, these norms acknowledge that premature release of ambiguous findings can cause confusion, misrepresentation, or unwarranted public reactions. Still, even this explanation struggles to account for why no agency issued a simple status update. The lack of even a generic statement analysis ongoing data under review or observations captured successfully was unusual. Silence invites interpretation, and in the modern information environment, it often amplifies suspicion rather than calming it. It is possible that the silence has no unified cause, that NASA was hindered by the shutdown ESA by internal scheduling delays, China by political considerations, the UA by resource limitations, and Russia by program restructuring. But the cumulative effect, especially given the rarity of interstellar visitors and the unique geometry of the 3I Atlas flyby, created the impression of absence where communication should have been abundant. In science, missing data can be as informative as released data. Silence itself becomes a phenomenon worth studying not because it implies a specific conclusion, but because it shapes the context in which evidence is interpreted. The absence of images, despite the near certainty that they exist, transformed public discussion from a purely scientific debate into a broader reflection on how institutions manage information during ambiguous events. The Mars flyby should have been a straightforward milestone in planetary astronomy. Instead, it became a reminder that interpretation depends not only on what we see, but on what we are shown and when. Until those images are released, the silence remains part of the story, shaping both the scientific narrative and the public imagination. Colour in astronomy is not merely an aesthetic detail, it is a diagnostic tool. A comet's hue encodes information about its chemical composition, the energy sources driving its activity, and the physical conditions around its nucleus. When observers first reported that 3I Atlas had shifted from a reddish tone to a distinct green glow between late August and early September, the change was more than cosmetic. It indicated a transformation in the comet's outgassing behaviour, at a moment when solar radiation should only have been moderately increasing. The shift demanded explanation, and as data accumulated, so did the contradictions. Under typical circumstances, a green coma around a comet is attributed to diatomic carbon C2. This molecule fluoresces strongly at around 510 nanometers when excited by ultraviolet radiation from the Sun. It is well understood, well documented, and has been the source of the classic green appearance in many bright comets observed from Earth. For a time, this standard explanation appeared sufficient for 3I Atlas as well. Early amateur photographs from Namibia showed a green halo enveloping a brighter core consistent with images seen in previous comet apparitions. However, the scientific analysis did not support the visual assumption. Spectroscopic studies conducted by university teams, including work led by Luis Salazar Manzano and colleagues, found that 3I Atlas was unusually depleted in carbon chain molecules. The C2 to CN ratio, a key metric used to classify comets, was among the lowest ever recorded. In practical terms, this meant that the primary molecule responsible for green coloration was essentially absent at detectable levels. A green coma without C2 presented a puzzle. The effect was visible, but the expected cause was missing. One proposed explanation was observational timing. Spectral measurements and broadband colour images may not have been taken simultaneously. If the comet's activity varied rapidly, it was conceivable that C2 production spiked during a window not captured by spectroscopic observations. Yet this hypothesis struggled to explain the consistency of the depletion across independent measurements and different instruments. Comet chemistry can fluctuate, but not typically with the speed or precision required to create such a discrepancy. Another possibility was that a different molecule was responsible for the green emission. Cyanogen CN fluoresces in the violet and blue-green regions under certain conditions. Data showed that CN production in 3I Atlas increased far more steeply than expected as the comet approached the Sun, following a power law with a heliocentric dependence exceeding what is normally observed. This raised the possibility that the green glow was a composite effect, modest CN emission combined with scattered dust and specific lighting geometry. Still, the CN-based explanation had gaps. CN is common in comets, but its emission typically does not dominate the coma's visible colour. For CN to be responsible for the observed green glow, 3I Atlas would need to possess an unusually nitrogen-rich composition relative to carbon, a configuration that does not align well with models of comet formation, but could be possible in rare circumstances. Some researchers pointed to the comet's interstellar origin as justification for its unusual chemistry. Unlike comets formed within the solar system, 3I Atlas originated around another star in a region where elemental abundances and chemical histories could differ dramatically. Galactic chemical gradients and the local effects of ancient supernovae could create environments where nitrogen-bearing molecules formed more readily than carbon chains. If 3I Atlas was indeed billions of years old, possibly twice the age of the Sun, it may have experienced cosmic ray processing and thermal cycling, unknown to the solar system's bodies. This line of reasoning offered plausible if speculative pathways toward explaining the anomaly, but it did not resolve the deeper inconsistencies. The green glow was strong and sustained, yet no spectroscopic signature matched it definitively. The molecule that should explain the colour was missing, and the molecule that could explain it only partially accounted for the phenomenon. Complicating matters further, another chemical anomaly appeared: the presence of nickel without corresponding iron. Nickel emission is rare but not unknown in comets. However, nickel almost always appears alongside iron given their common formation pathways in stellar environments. In 3C Atlas, nickel production increased by a factor of 25 within 1 month, while iron remained undetected until much later, and even then only at extremely low levels. This unexpected separation raised questions about the physical processes occurring on the comet's surface. One natural explanation was that nickel carbonyl, a volatile compound formed from nickel and carbon monoxide, could sublimate at far lower temperatures than metallic or mineral-bound nickel. Given that 3I Atlas was unusually rich in carbon monoxide and carbon dioxide, nickel could be selectively lifted off the comet's surface. Yet this mechanism requires a mineralogical configuration that has never been observed in any solar system object. It also requires a fine balance between temperature mineralogy and local chemistry that would be extraordinary even for an exotic interstellar body. The green glow, the carbon chain depletion, the unusual CN production, and the nickel heavy emission profile formed a pattern of chemical behaviour that resisted straightforward interpretation. Each anomaly could be explained individually through tailored natural mechanisms, but together they raised a broader question: how many unlikely conditions must coincide before the collection of explanations becomes more improbable than the anomalies themselves? Scientists familiar with Bayesian reasoning pointed out that each unusual observation decreased the likelihood of a simple natural model being correct. When phenomena become statistically independent and individually unlikely, their combined probability becomes extremely small, suggesting that either they share a single underlying cause, or the assumptions guiding the analysis require revision. Still, the prevailing view within the scientific community remained cautious. Interstellar objects represent an extremely small and poorly understood sample. With only 3 such objects ever detected, the range of possible behaviours and compositions remains largely unknown. It is entirely plausible that 3 Atlas simply lies at the extreme edge of natural variance. Whether the green glow indicates exotic chemistry, a poorly understood fluorescence mechanism, or a combination of multiple subtle processes, its significance lies less in any one theory, and more in its contribution to a growing recognition. Atlas does not neatly resemble any comet we've studied before. Its behaviour challenges assumptions, exposes gaps in models, and invites careful reconsideration of what ordinary means when dealing with materials older and more distant than our Sun itself. In the end, the green coma is neither evidence of the extraordinary nor proof of the mundane. It is a reminder that the universe often communicates in signals that do not yield to simple interpretation, and that our understanding remains provisional, open to revision as new data emerges. The closer scientists looked at the strange behaviour of 3I Atlas, the more the available explanations began to fracture. Instead of converging toward a single coherent model, the data splintered into competing interpretations, leaving researchers to sift through ambiguities that deepened rather than clarified. The debate surrounding the elongated shape captured by the Perseverance rover exemplified this widening divide. Conventional imaging physics provided one possible answer, yet alternative analyses highlighted inconsistencies that refused to disappear. When images from different observers suggested a white-centered structure wrapped in green emission, the question ceased to be about photographic artifacts and shifted toward whether the object's physical properties might genuinely differ from anything previously catalogued. In a scientific environment accustomed to mapping anomalies onto known categories, Atlas posed the opposite challenge. It destabilized the categories themselves. This persistent mismatch between expectation and observation only grew sharper as major space agencies withheld their highest resolution data. The silence created a paradox. On one hand, agencies argued that government shutdowns, personnel shortages and processing delays made immediate release impossible. On the other, the global alignment of that silence across NASA, ESA, China and the UAE raised suspicion, precisely because these institutions normally compete for visibility. When agencies with divergent geopolitical interests simultaneously failed to publish images that had been anticipated for months, it invited interpretations that no one had planned for. The lack of transparency created a vacuum, and in that vacuum, independent observers began to shape the public narrative. Amateur astronomers stepped into this informational void, often unintentionally. Their equipment was not designed to capture a high-velocity interstellar object tens of millions of kilometers away, and yet the very attempt highlighted how little the public had been given to work with. When one observer produced an image that appeared to show angular structure, the reaction revealed a deeper issue than the image itself. It exposed a growing cultural gap between institutional authority and public scrutiny. In earlier eras, opaque scientific processes were accepted as necessary. Today, people expect data, not reassurance. When institutions hesitate to release evidence, speculation expands into the space they leave behind. In that sense, the scientific controversy around Atlas was not merely about a comet. It became an illustration of how credibility erodes in the absence of openness. As these debates intensified, attention shifted toward a more fundamental problem: the object's chemical profile. The detection of carbon dioxide outgassing at distances where sublimation should not occur challenged established models of thermal physics and cometary bodies. Traditional comets follow predictable patterns. They remain inert in deep space and only become active when solar radiation provides enough heat to vaporize surface ice. Atlas violated this rhythm by turning on far too early, as if driven by internal processes rather than external heating. This persistent activation suggested either an unusually volatile composition or some mechanism capable of releasing gas without the expected thermal conditions. Each new measurement complicated the previous ones, revealing a pattern of behavior so irregular that every natural explanation had to be re-examined from first principles. The opacity surrounding the object's mass added another layer of uncertainty. Estimates were so inconsistent, ranging from half a kilometre to over 10 kilometres in diameter, that it became difficult to evaluate its true scale. A massive nucleus would imply statistical improbability. Such large interstellar objects should be exceedingly rare. A small nucleus with extremely bright outgassing, however, would imply an activity level that defies chemical expectations. In both scenarios, the object sits uncomfortably at the edge of what current astrophysical models can accommodate. The question increasingly resembled a puzzle, with no available pieces and object either too large to fit known distributions or too active to match known physics. The trajectory of Atlas compounded these difficulties. Its path through the inner solar system appeared to align with startling precision with multiple planetary orbits. Though coincidence remained a plausible explanation, the statistical odds were low enough to attract serious attention. Scientific models thrive on probability, not certainty, and when probabilities become strained, alternative hypotheses gain legitimacy. Atlas forced researchers to confront the possibility that conventional randomness may not fully account for its behavior. Whether this indicated unknown gravitational interactions, errors in modeling, or something more deliberate remained unresolved. What mattered was that the trajectory itself refused to behave like a typical interstellar flyby. The long period during which Atlas would disappear behind the Sun presented the most troubling variable. Perihelion is always a point of significant activity for comets, but in this case, it also represented a period of total observational blindness. For nearly a month, Earth would be unable to monitor changes in brightness outgassing, or trajectory leaving scientists with only indirect models. This vulnerability came at the worst possible time, just as the object approached the region where many of its anomalies might intensify. The orbital geometry created a moment in which predictions would outpace observations, and any unexpected behaviour would remain hidden until December. The scientific implications were clear. For the first time since Atlas's discovery, researchers would be left to wait without data. As the object approached that critical window, the debate surrounding Atlas became less about what was known and more about what remained unknowable. Each new observation fractured existing explanations without offering replacements. Each silence from official channels deepened public doubt. Each amateur attempt to compensate underscored the limits of available information. Atlas, whatever it may be, forced a rare and uncomfortable acknowledgement within the scientific community. Sometimes the universe delivers puzzles that resist immediate interpretation. The controversies surrounding shape chemistry, mass and trajectory were not signs of failure but symptoms of discovery, reminders that science progresses by confronting the unexplained, not avoiding it. The debate surrounding 3I Atlas shifted significantly once researchers began to examine its non-gravitational behaviour. In celestial mechanics, the motion of an object is governed almost entirely by the gravitational influence of the Sun, planets, and in rare cases by massive asteroids. Deviations from this predictable path typically indicate outgassing jets of evaporating ice that act like tiny thrusters and push a comet slightly off course. These effects are well studied and appear consistently in models of cometary motion. However, in the case of 3I Atlas, the recorded deviations were both too subtle and too inconsistent to match the expected signature of natural outgassing. This mismatch forced scientists to question whether the object was merely an unusually active comet or whether an entirely different mechanism was influencing its trajectory. Early analysis from ground-based telescopes suggested that the comet was accelerating in ways that did not align with the observed patterns of gas release. Normally, when outgassing is responsible for acceleration, a correlation exists between the direction of the gas jets and the direction of the resulting force. But Atlas exhibited thrust-like behaviour in directions where gas emissions were either weak or non-existent. Conversely, in regions where spectroscopic data showed substantial gas release, the object did not accelerate in the corresponding direction. This contradictory behaviour raised the possibility that Atlas's activity was not driven solely by surface sublimation, but perhaps by internal processes that redistributed pressure or energy in ways that have not been documented before. This ambiguity grew sharper when researchers examined the timing of the acceleration. Comets typically display increased non-gravitational forces as they approach the Sun and begin to sublimate rapidly. Atlas, however, demonstrated measurable deviations in its path when it was still well beyond the distance at which significant thermal activation should occur. The object behaved as if it were being influenced by a mechanism independent of solar heating. Even if exotic volatiles like carbon monoxide or carbon dioxide were responsible, the magnitude of the observed accelerations did not fit with established models of how gas vents operate in low-temperature environments. The uncertainty surrounding Atlas's mass further complicated the situation. A larger nucleus would require far more force to change its trajectory than the observed outgassing could plausibly provide. Conversely, a very small nucleus would be highly susceptible to even weak jets, but such an object would produce a brightness profile that contradicted the measurements recorded by the James Webb Space Telescope and several large ground-based observatories. This placed Atlas in a difficult position. It either had to be large and accelerating without sufficient force, or small and glowing far brighter than expected. Each option challenged a different pillar of cometary physics. As scientists attempted to reconcile these contradictions, a separate tension emerged regarding the object's approach toward perihelion. From mid-October to late November, the comet would pass behind the Sun from Earth's perspective, making direct observation impossible. During this period, solar gravitational influence would be at its peak, and many comets undergo rapid changes in activity. Some fragment, some brighten dramatically, others exhibit sudden jets, but Atlas's behaviour leading up to this invisibility window gave no reliable indication of what would happen during the period when it could not be monitored. For an object already defying expectations, this created a moment of genuine uncertainty for researchers who were accustomed to modelling comet behaviour with high precision. The disappearance of Atlas behind the Sun introduced a critical vulnerability: the inability to immediately identify any changes in its trajectory. If its path after perihelion differed even slightly from predictions, the implications for non-gravitational forces would become far more significant. A deviation beyond the expected error margin would suggest either that the object experienced internal structural changes during its solar encounter, or that previously undetected forces were acting upon it. Some scientists expressed concern that without real-time observational data, the ability to validate or correct orbital models would be delayed by weeks, leaving room for large uncertainties to accumulate. This period of forced observational silence also had public consequences. For months, skepticism had surrounded the absence of high-resolution images from Mars-based instruments. As Atlas approached perihelion, online speculation grew further fueled by the lack of new data and the increasing complexity of the object's behaviour. In scientific discourse, silence is often interpreted cautiously. In public discourse, however, silence is frequently interpreted suspiciously. The inability to observe Atlas during one of its most critical phases deepened this divide, with some commentators arguing that institutional reluctance to release information was deliberate rather than circumstantial. Meanwhile, astronomers attempting to maintain scientific rigour faced an unavoidable reality: the available datasets contained gaps too large to fill with confidence. The existing measurements of luminosity coma composition, emission rates, non-gravitational acceleration and thermal activity all pointed in different directions, making it difficult to construct a unified model. Researchers accustomed to resolving contradictions within narrow margins found themselves instead confronting contradictions that appeared fundamental. The possibility that Atlas represented a class of interstellar objects entirely unlike those previously encountered gained traction. Rather than forcing Atlas into the framework of cometary physics, some researchers argued that new classification might be needed, one that accommodates objects with unusual mineralogy, volatile mixtures, and internal thermochemical dynamics. This position did not imply that the object was artificial or engineered. Rather, it acknowledged the limited sample size of interstellar visitors. With only 2 confirmed interstellar objects before Atlas, the range of possible structures and behaviours remains almost entirely unknown. Yet the very fact that Atlas challenged so many assumptions made it scientifically valuable. It exposed weaknesses in existing models, highlighted the limitations of remote spectroscopy, and demonstrated the need for coordinated multi-agency observation strategies during rare astronomical events. It also underscored how easily uncertainty can accumulate when small deviations interact with incomplete data. The object itself became a reminder that scientific understanding is provisional, evolving not through confirmation but through the careful interrogation of anomalies. As Atlas approached perihelion, the scientific community braced for a period of enforced patience. Whether the object would fragment, brighten, or alter course remained unknown. Whether its chemistry would remain stable or undergo rapid transformation remained uncertain. The only certainty was that new data in December would either resolve the contradictions or amplify them further. In that sense, Atlas functioned not only as an object of study, but as a test of the scientific method itself, an opportunity to confront the unknown without prematurely imposing coherence upon it. As 3C Atlas moved deeper into the inner solar system, attention increasingly shifted toward the patterns emerging from its multi-wavelength observations. Data from infrared, optical, and ultraviolet instruments began to reveal divergences that could not easily be reconciled by any single physical model. In typical comet studies, different observational domains complement one another, offering a coherent picture of temperature composition, surface activity, and dust production. For Atlas, however, each observational method appeared to pull the interpretation in a different direction, as though researchers were attempting to assemble a puzzle with pieces sourced from entirely different sets. Infrared measurements suggested that the object's surface temperature was inconsistent with its observed level of outgassing. At distances where sublimation of carbon dioxide should be minimal, the James Webb Space Telescope detected gas production at levels that would ordinarily require much higher thermal input. This discrepancy raised questions about the internal structure of the object. A porous interior filled with supervolatile compounds could theoretically release gas at lower temperatures, but such a configuration would need to be unusually fine-tuned. Most known comets release volatiles in a gradual thermally driven pattern. Atlas instead exhibited episodic bursts of activity that did not correlate with smooth changes in solar heating. Optical observations provided another layer of contradiction. Ground-based telescopes recorded brightness fluctuations that did not align with typical rotational modulation. Comets often display periodic variations in brightness, as their irregular shapes rotate, exposing active regions to sunlight. In Atlas, however, the fluctuations appeared quasi-random, as though activity was occurring at irregular intervals rather than being tied to rotation. This raised the possibility that the nucleus was either tumbling chaotically, or that its active regions were distributed in a highly asymmetric manner. Neither scenario fit well with the limited photometric data suggesting mild rotational behaviour. The ultraviolet spectrum added further complications. Certain ion emissions commonly used to infer composition did not appear at expected ratios. Specifically, the lack of strong hydroxyl emissions, a primary indicator of water sublimation, suggested that water ice was not a dominant volatile in the object. This alone would not be unusual for a distant comet. Water sublimation becomes significant only at closer solar distances. Yet the strength of carbon dioxide and carbon monoxide emissions contradicted the low infrared temperature measurements. The object seemed to release gas in patterns more consistent with internal pressure or chemical reactions than with passive thermal sublimation. These inconsistencies led some researchers to revisit the possibility of internal heating mechanisms. One hypothesis proposed that radioactive decay within the interstellar object could generate sufficient internal heat to trigger volatile release. However, the level of radioactivity required would be difficult to reconcile with what is known about the distribution of radionuclides in planetary bodies formed around other stars. Another model suggested that the object might have an unusually dark subsurface layer, capable of absorbing significant amounts of faint solar radiation and distributing the heat internally. But this too required assumptions unsupported by available data. As the inconsistencies accumulated, the question of shape re-emerged with greater urgency. The elongated streak captured by Perseverance had already sparked debate, but without high-resolution images, researchers were forced to rely on indirect methods to infer the nucleus's geometry. Thermal models suggested that a highly elongated body would exhibit distinct temperature gradients along its axis, producing asymmetric outgassing patterns. Some of the acceleration anomalies might be explained by such a symmetry. Yet conflicting optical brightness curves made it difficult to confirm whether Atlas was elongated, irregular, or perhaps composed of multiple, contact binary lobes like Comet 67P Churyumov-Gerasimenko. The uncertainty became even more pronounced when researchers considered the role of external forces. Solar radiation pressure is typically negligible for massive bodies, but if Atlas was significantly less dense than expected, perhaps due to a highly porous interior, the influence of radiation pressure might become non-trivial. This scenario would help explain some of the minor non-gravitational accelerations, yet it clashed with mass estimates derived from its brightness and observed gas production rates. A low-density object should release dust differently, and the observed dust-to-gas ratio did not match the patterns typical of porous comets. Dust analysis introduced its own difficulties. Some instruments indicated unusually large dust grains being ejected from the nucleus grains that would require substantial energy to lift. Smaller comets can produce such grains, but typically only near perihelion when solar energy input is high. Atlas produced them earlier at much lower temperatures. This inconsistency suggested that either the dust grains were being produced by fracture events, triggered by internal stresses or the nucleus-housed volatile pockets capable of generating sudden, forceful jets. Both explanations carried implications that were difficult to verify without direct imaging. These accumulating ambiguities reinforced a broader realization within the scientific community. The behavior of interstellar objects may not align with expectations shaped by solar system comets. The field currently relies on a data set defined by bodies formed in the Sun's protoplanetary disk. Interstellar planetesimals could reflect different chemical histories, radiation exposure, and gravitational environments. While this explanation accommodated the strangeness of Atlas without resorting to extraordinary claims, it also required a willingness to operate without established frameworks. The scientific instinct to categorize and compare became a liability in a situation where analogues were limited or non-existent. The approach of perihelion intensified the need for clarity, while simultaneously limiting the possibility of obtaining it. Once the object crossed behind the Sun, Earth-based observations ceased entirely. This period of enforced absence meant that scientists could only model the object's behavior, projecting forward based on incomplete data. These projections varied widely, depending on which anomalous property was weighted most heavily: thermal activity, chemical composition, non-gravitational acceleration, or brightness fluctuations. The wide divergence of predictions reflected the unresolved tension at the heart of Atlas's behavior. No single model could accommodate all the observations without contradiction. As the silence lengthened, the scientific community found itself in an unfamiliar position. Instead of refining models through a stream of continuous data, researchers were confronted with a rare moment where theory had to stretch across an informational gap. The most optimistic projections assumed that Atlas would behave like an extreme, but still natural comet brightening near perihelion, shedding more gas and perhaps fragmenting. The more conservative projections emphasize caution, noting that unpredictable interstellar objects could deviate in ways not covered by solar system analogues. What united these perspectives was the recognition that December would deliver the first meaningful verdict. Once Atlas emerged from behind the Sun, its trajectory, brightness, and activity would either reinforce existing interpretations or complicate them further. Until that moment, the scientific narrative surrounding Atlas remained suspended. Each piece of data illuminated one aspect of the object, while obscuring another, creating a mosaic that resisted neat resolution. Whether Atlas ultimately behaved like a natural comet or continued to defy expectations, it had already demonstrated something significant. The limitations of existing cometary models become most evident not in predictable observations, but in the anomalies that force those models to confront the unknown. In the final weeks before 3 Atlas emerged from behind the Sun, the conversation around the object shifted toward a subtler, but equally important dimension: the nature of scientific uncertainty itself. Unlike spacecraft missions with controlled parameters, interstellar objects arrive unannounced, uncalibrated, and unrepeatable. Each observation is a single data point in a sequence that cannot be recreated, making gaps in the timeline especially problematic. The passage behind the Sun magnified this issue dramatically. For nearly a month, the object became invisible to every Earth-based telescope, severing the continuity that researchers rely on to track evolution in activity, brightness, and motion. This enforced blindness underscored a persistent vulnerability in the study of transient cosmic phenomena. During this interval prediction, models diverged more sharply than before. Some researchers emphasized the possibility of fragmentation at perihelion, citing the behavior of sun-grazing comets recorded by SOHO over the past decades. Many of those objects disintegrated when subjected to strong solar radiation, producing a rapid drop in brightness, followed by complete disappearance. Yet Atlas was not a sungrazer in the classical sense. Its perihelion distance of 136 AU was far beyond the extreme environments that typically destroy comets. Models based on structural strength therefore suggested that catastrophic breakup was unlikely. Still, the steep power law dependencies seen in the nickel and cyanide emissions left room for the possibility that internal processes might push the object into unstable behavior under rapid heating. Without direct measurements, both scenarios could be defended. Trajectory predictions were similarly bifurcated. Teams working with orbital dynamics argued that any deviations from purely gravitational motion would remain minor, consistent with typical outgassing forces seen in comets. Their models assumed that jets of sublimated material would maintain roughly symmetric distribution across the nucleus. But alternative analyses pointed to the potential for highly directional jets, particularly if the nucleus had an elongated shape or significant internal pressure differentials. Under these circumstances, even small anisotropies could accumulate into measurable shifts in trajectory. The disagreement reflected the larger uncertainty about the nucleus's geometry and the location of active regions, factors that remained impossible to determine with precision. Chemical behavior projections created yet another axis of uncertainty. If the nickel emissions continued scaling with heliocentric distance, as early observations suggested, then perihelion should produce a detectable spike in metal line intensities. But this linear expectation assumed that sublimation or chemical release would proceed uninterrupted under increasing heat. Some researchers proposed threshold effects activation points, at which materials transition from slow release to rapid discharge. These effects are common in physical chemistry, but applying them to interstellar objects required caution. Since no direct measurements of surface composition existed, all such projections rested on untested assumptions. Others warned that perihelion could just as easily lead to depletion of volatile rich layers, causing emissions to plateau or even diminish. The range of plausible outcomes was broad, leaving the scientific community without consensus. Meanwhile, the role of external spacecraft became central. Instruments aboard Zoho Parker Solar Probe and ISA's JUICE spacecraft represented the only sources of potential perihelion data before Earth regained a line of sight. But these platforms were not designed with interstellar object monitoring in mind. SOHO's coronagraphs offer valuable insights into brightness, evolution, and dust production, yet their spatial resolution is limited. They can reveal whether a comet brightens fragments or develops a significant tail, but cannot resolve structural details of the nucleus. Parker Solar Probe's imaging capabilities, though more advanced, are constrained by mission priorities centered on solar physics. Any images of Atlas would be peripheral, incidental, and dependent on complex pointing schedules. JUICE promised the highest quality data, yet even its instruments could not observe perihelion, directly leaving a temporal gap between maximum activity and spacecraft visibility. The public following the story through scientific blogs, news outlets, and social media reacted predictably to this void. Without real-time updates, speculation flourished. Some interpreted the lack of information as evidence of dramatic events unfolding unobserved. Others assumed that the absence of data meant that nothing noteworthy had occurred. Neither interpretation was grounded in evidence, but both reflected a broader challenge in contemporary science communication when observation pauses, narrative fills the space. Some researchers took this as an opportunity to emphasize the provisional nature of scientific conclusions, reminding audiences that not knowing is often part of the process. Others expressed concern that this gap might fuel misinformation once new data began to surface. Beyond public speculation, professional discourse turned inward, reflecting on how to prepare for the object's reappearance. Observatories around the world scheduled early December observation, run securing telescope time to capture the first post-perihelion images. Teams refined their photometric pipelines in advance, anticipating the need for rapid processing to update orbital solutions. Spectroscopic facilities organized coordinated campaigns intending to measure chemical signatures as soon as Atlas emerged from solar glare. The focus rested not only on the object itself but on the methods required to interpret unfamiliar data. This preparation served as recognition that interstellar objects are becoming a new frontier in astronomy, one that demands revised protocols and more adaptive strategies. As the days passed, attention also turned to the historical record. Researchers revisited observations of 1I Oumuamua and 2I Borisov, comparing their pre- and post-perihelion behavior to what might be expected of Atlas. Oumuamua, though lacking a visible coma, displayed a post-perihelion non-gravitational acceleration that remains unexplained. It reminded astronomers that anomalous behavior can emerge only after solar heating peaks. Borisov, by contrast, behaved like a conventional comet, fragmenting slightly, but maintaining predictable dynamics. These prior cases became frameworks, though imperfect ones, for predicting Atlas's fate. If Atlas mirrored Borisov, researchers might expect a relatively ordinary pattern of increasing activity followed by gradual fading. If its behaviour resembled Oumuamua, more unconventional changes could follow chemical shifts, acceleration anomalies, or unexpected dimming. This comparative approach highlighted a deeper issue: the sample size of interstellar objects remains too small to establish general rules. With only 2 prior examples and both exhibiting dramatically different characteristics, no shared behavioural template exists. Atlas thus functioned as a test of broader hypotheses about interstellar diversity. Its post-perihelion data would provide the most direct evidence yet about whether interstellar objects follow predictable categories, or whether each represents a unique, unrepeatable expression of its origin system. The anticipation surrounding Atlas's reappearance was therefore not merely a reaction to its anomalies, but part of a larger scientific effort to understand the variability inherent in material formed under unknown astrophysical conditions. By late November, the anticipation settled into a quiet waiting. Research teams finalized their models, prepared observational campaigns, and acknowledged privately that their predictions might be rendered obsolete within hours of new data. It was an unusual moment in contemporary astronomy, one shaped not by continuous data streams, but by the absence of them. The discipline, often defined by its reliance on empirical observation, found itself temporarily suspended in conjecture. When Atlas returned to view, the first measurements would carry disproportionate weight capable of confirming or overturning weeks of speculation. The expectation was not for definitive answers, but for clarity, some indication of whether the object's earlier behaviour represented the rule or the exception. And as December approached, the scientific world prepared to step back into the light alongside Atlas itself, ready to learn what had transpired in the weeks when the sun stood between observer and object. When 3C Atlas finally approached the point in its orbit where it would become visible again, a quiet tension formed across observatories and research teams. The preceding weeks had been marked not by new discoveries, but by the awareness of how little could be confirmed without direct observation. Astronomers understood that the first data points after solar conjunction would carry an unusual weight, not because they would immediately resolve every open question, but because they would determine which explanations remained viable and which would become increasingly difficult to defend. In astronomy, the return of visibility often signals the resumption of routine analysis. In the case of Atlas, it signalled the reopening of a scientific case file temporarily sealed by geometry alone. Planning for this moment had been unusually coordinated. Observatories typically operate under competitive scheduling pressures, but the prospect of capturing a rare interstellar object transformed the dynamic into one of mutual reinforcement. Facilities in the southern hemisphere prepared to secure the earliest views, while northern observatories waited for the object's rising position to shift into their range. Teams responsible for spectroscopic instruments refined their exposure strategies to optimize for faint emissions that might indicate residual heating or continued chemical processes induced by perihelion. Photometric teams concentrated on brightness evolution, hoping to determine whether the object had fragmented, brightened, dimmed, or remained stable. Each group understood that even an imperfect first glimpse could influence how subsequent observations were interpreted. The expectations surrounding fragmentation were particularly strong. Thermal stress remains one of the dominant factors in determining cometary stability, and for a body as chemically unusual as Atlas, predictions were made cautiously. Classical models suggested that the object's perihelion distance was not extreme enough to induce catastrophic rupture. But the unusual nickel and cyanide behaviours raised the possibility that internal heat distribution might not follow expected patterns. If volatiles were concentrated in localized reservoirs rather than distributed uniformly beneath the surface, asymmetric pressure release could produce sudden structural failure. Evidence of fragmentation would therefore imply that Atlas possessed a weaker internal cohesion than some hypotheses predicted. The absence of fragmentation, by contrast, would strengthen interpretations that emphasized rigidity, elongated geometry, or a composition capable of resisting significant thermal gradients. Brightness served as the most immediately accessible indicator. Many researchers anticipated that Atlas would appear brighter than before perihelion. due to increased surface exposure and expanded coma formation. A sudden drop in brightness, however, would imply either fragmentation into numerous smaller pieces or rapid depletion of volatile material near the surface. In both cases, the brightness curve would hold diagnostic value. The challenge lay in avoiding overinterpretation of early measurements, since atmospheric conditions, viewing angles and instrument sensitivity could all create the appearance of variation where none existed. A single night's data could not define the object's post-perihelion state. Only a sequence of observations would reveal genuine trends. Trajectory measurements were treated with comparable importance. Pre-perihelion orbital solutions were well constrained, allowing astronomers to predict where Atlas should appear once it emerged from conjunction. If the observed position differed from predictions by more than the uncertainties allowed, the discrepancy could indicate non-gravitational forces acting on the object during or after perihelion. These forces could originate from normal cometary jets or from more exotic processes. Distinguishing between the two required analysing not just the magnitude of deviation, but its direction. A shift consistent with solar-driven outgassing would align with physical expectations. A deviation orthogonal to expected vectors or larger than typical outgassing forces would require deeper analysis. That possibility was not treated as sensational. It was simply recognised as a scenario that models needed to accommodate if data pointed that way. Chemical signatures represented another key objective. If the steep power law dependencies observed before perihelion continued afterward, researchers expected elevated line intensities for nickel and cyanide. But this depended on whether the same processes were still active. Strong emissions could indicate that perihelion ignited sustained material release, perhaps exposing deeper layers, or initiating new reactions under high thermal stress. Conversely, a sudden drop would suggest that the earlier rise in emissions stemmed from a finite reservoir of volatile material that was now depleted. In either case, the spectroscopic data would provide a direct window into the object's evolving composition, helping determine whether the earlier anomalies represented stable characteristics or temporary phenomena linked to a limited phase of activity. While researchers prepared their instruments, a separate conversation unfolded within the community about how to contextualize whatever came next. The contrasting interpretations that had defined months of debate had made it clear that observational gaps create interpretive divergence, not because of error, but because of necessity. Without continuous data, theories expand to fill the silence. Some analysts frame this as a feature, rather than a flaw, a natural consequence of investigating an object from another star system under incomplete conditions. Others argue that interstellar objects require new methodological frameworks altogether, ones that recognize the limitations of Earth-based geometry and incorporate contingency planning for inevitable periods of observational blindness. The philosophical question underlying these discussions was deceptively simple. What does it mean to study something that might never behave like anything previously recorded? Atlas had already shown that assumptions drawn from solar system objects could not be applied directly. Its chemistry, brightness evolution, and statistical improbabilities had challenged standard categories without fully overturning them. The post-perihelion data therefore represented not just information about the object itself, but an opportunity to refine how theories accommodate edge cases. Scientific models evolve through both confirmation and contradiction. And Atlas, regardless of its ultimate classification, was proving itself valuable precisely because it resisted easy categorization. By the final days of November, this anticipation settled into a structured patience. Observatories awaited clear skies, instruments awaited calibration runs, and researchers awaited the first faint return of an object that had slipped beyond observational reach for nearly a month. In that waiting, a subtle shift occurred. The focus moved away from the debates that had occupied earlier stages and toward the broader significance of the encounter. Whatever Atlas revealed after perihelion fragmentation stability, chemical transformation, or familiar behaviour would become part of a growing archive of interstellar encounters that future astronomers would study. Even uncertainty properly documented would have value. The moment of reappearance would not provide all answers, but it would open the next phase of understanding grounded once more in observation rather than projection. As additional nights of post-perihelion data accumulated, researchers finally gained enough measurements to shift from preliminary impressions to genuine interpretation. The early ambiguity surrounding brightness, spectral lines and trajectory slowly gave way to clearer patterns. Yet clarity did not mean simplicity. Instead, it revealed how complex and layered 3i Atlas's evolution had become. Rather than resolving the anomalies that defined the pre-perihelion phase, the new data broadened the scientific discussion, offering evidence that could support multiple frameworks depending on the assumptions applied. In this regard, Atlas continued to function less as a singular answer and more as a case study in the limits of astronomical inference. By mid-December, brightness trends had stabilized to the point that researchers could begin constructing a reliable post-perihelion light curve. The data suggested a moderate decline from the early December spike, consistent with the cooling of the nucleus as it receded from its closest approach to the Sun. This behavior resembled classical comets, which often show rapid brightening near perihelion, followed by a gradual fade as the energy driving outgassing diminishes. However unlike typical comets, Atlas did not exhibit the clear signs of fragmentation that many had speculated might occur. No abrupt dips in brightness appeared, and no secondary nuclei were detected in either amateur or professional images. This absence did not prove structural rigidity, but it did indicate that the object had sufficient cohesion to withstand perihelion activity without catastrophic disruption. The next step involved refining the trajectory. With more positional measurements now available, orbital analysts applied updated solutions to determine whether Atlas had deviated from predicted paths. The early data suggested small but measurable variations relative to pre-perihelion projections. Whether these deviations fell within the expected range of natural outgassing effects became the central point of analysis. In many comets, jets of sublimated material create thrust that subtly alters their motion over time. The magnitude of Atlas's deviations could be explained by this mechanism if one assumed significant asymmetric activity on the sunward hemisphere. But a different interpretation emerged among some researchers that the magnitude and direction of the deviation were slightly inconsistent with what would normally result from outgassing patterns predicted by solar illumination. This did not prove that an additional force was involved, but it reopened debates about how well the standard thermal model applied to interstellar objects, whose compositions and structures might not match those formed in the early solar system. Chemical analysis proved even more complex. As more post-perihelion spectra were collected, researchers noticed that nickel emissions, though diminished, compared to peak pre-perihelion values, remained detectable at levels higher than expected. The persistence of these lines suggested that the processes producing nickel release were not limited to a narrow perihelion window. Cyanide emissions also remained elevated, though their ratios fluctuated across different observations. This variability sparked debate. One interpretation held that both nickel and cyanide were tied to volatile-rich surface reservoirs that continued releasing material as sunlight penetrated deeper layers exposed by perihelion activity. Another argued that the fluctuating ratios pointed to underlying heterogeneity within the nucleus pockets of differing chemical composition activated at different times. A third, more cautious perspective emphasized instrumentation differences, atmospheric conditions, and data processing inconsistencies that could create artificial variability. Each interpretation had merit, and no single data set was sufficient to resolve the disagreement. The persistence of nickel emission was particularly significant. If the early increase represented the thermal liberation of nickel-bearing compounds, the post-perihelion decline should have sharply mirrored the distance-based power law, relationship observed earlier. Instead, the decline appeared nonlinear. Some researchers interpreted this as evidence that whatever chemical reactions drove nickel release were more complex than a simple sublimation gradient. Others proposed that the surface may have reached a new equilibrium after perihelion, in which exposed layers continued contributing to emissions, even as overall thermal input decreased. The complexity underscored the challenge of analysing an object whose mineralogical foundations remained unknown. Perhaps the most unexpected development came from re-evaluations of archival data. As new measurements accumulated, several research groups revisited earlier interpretations comparing pre- and post-perihelion patterns side by side. This comparative method revealed that certain anomalies only appeared anomalous when viewed in isolation. For example, the nickel-to-iron ratio seemed extreme when considered without context, but when compared against more recent data, the ratio appeared to fluctuate more widely than an initial report suggested. This did not remove the anomaly entirely, but it reframed the question, rather than asking why nickel was so abundant relative to iron. Researchers began asking why the ratio varied over time and what internal processes might allow such variability. The shift in framing was subtle but important. It transformed the debate from one focused on singular oddities to one focused on dynamic behaviour. The absence of fragmentation, modest trajectory deviations, and lingering chemical activity all pointed toward an object that resisted straightforward categorization. Atlas behaved partly like a comet, partly like an unknown class of interstellar body, and partly like something that challenged the assumptions built into existing models. But none of these behaviours demanded exotic explanations. The scientific value of Atlas lay not in supporting any particular theory, but in illuminating the limitations of current frameworks. Interstellar objects were still rare enough that each new example functioned as a unique data point complicating efforts to build generalized models. The variability observed across Oumuamua, Borisov and Atlas suggested that diversity might be the norm rather than the exception. By the end of the first full post-perihelion month, researchers accepted that Atlas would remain an object of interpretation rather than a solved case. The data gathered were substantial, but the object's nature depended on assumptions that could not yet be verified. Lacking a direct sample, high-resolution imagery or continuous coverage, astronomers were forced to draw conclusions from incomplete signals, brightness curves shaped by atmospheric distortion, spectral lines filtered through instrument noise and trajectories reconstructed through iterative modelling. The process was imperfect, but it reflected the reality of studying an interstellar traveller whose brief passage offered only glimpses of its deeper structure. In that sense, Atlas became less a mystery to be solved, and more an example of how science progresses through refinement, comparison, and recognition of uncertainty. Its passage through the solar system reminded researchers that the unknown is often not a problem, but a condition, an invitation to continue observing, questioning, and revising. When future interstellar objects arrive, the lessons learned from Atlas will guide the approach, inform expectations, and shape the models into which new data will be placed. What Atlas ultimately represented scientifically was not a singular anomaly, but a preview of a wider and more diverse cosmic population waiting to be studied. And now, Traveller. Our path reaches its quiet edge. We have followed this strange visitor across worlds and shadows, watching its shape blur, divide, and come back together in our minds. What began as a single glitch in a frame has become something larger, a reminder that the universe rarely reveals itself cleanly. It speaks in fragments, in colours that shift, in silences that deepen rather than explain. As we drift here at the end of this story, you and I have done what humans have always done. Beneath the stars we looked, we wondered, and we accepted that not every answer arrives when we want it to. Some mysteries move on their own timelines. Some keep their distance. Some choose to be understood only slowly, like comets warming in the dark. But there is something comforting in that observer, in knowing that even when we cannot hold the full truth, we can still feel its presence passing by. We can still share the act of looking up, fragile and curious, carried by the same cosmic tide that carries through Atlas itself. Thank you for drifting through this with me tonight. If this story found you at the right moment, you're welcome to wander with me again. Whenever the sky feels heavy with questions, rest well, traveller. Stay curious.